Alright, so this is section 10.2, part 1. In this video, we're going to talk about significance and also understanding what a p-value is. We'll also discuss how we find the p-value, how we use it, and then also just some examples in future videos. Alright, so the first thing we want to make sure we understand is this idea of statistical significance. And we've actually been working with this concept, but we haven't used this name. We've talked about statistical significance when we've talked about something being considered unusual or unlikely. And so that's how we're going to define this. And this is our definition that our interactive textbook also uses. So it says that when observed results are unlikely under the assumption that the null hypothesis is true, that's when we have statistical significance. In other words, if it would be unusual, we say it's statistically significant. So if my chances of getting a particular sample value, so let's say since we're working with proportions in section 10.2, let's say I get a sample proportion of 60%, but I'm expecting 50%, then I need to know how likely would it have been for me to get 60% instead of 50% if it should have been 50. And if it's, how unlikely is that? That helps me figure out whether or not I have statistical significance. We're going to figure out the ways of getting this, and luckily our calculator is going to do all the math for us. But we need to be able to identify that cutoff, which we've been using 0.05. We've said that something's unusual if there's less than a 5% chance of it happening. Well, now we may use 0.05 or we may use another value, and that's going to be our significance level. So we talked about that in section 10.1. So if you missed that video, go back and watch the videos for section 10.1 where I talk about the significance level. This is statistical significance is our significance level. These go together. So if we're less than our significance level, we're unusual enough. We didn't expect that to happen. And it's unusual enough for us to say we no longer believe the null hypothesis. That's going to be our kind of big takeaway. All right, so here's our definition for a p-value. Again, just from our textbook, we're told that a p-value is the probability of observing a sample statistic as extreme or more extreme than one observed, assuming the null hypothesis is true. And I feel like there should have probably been some commas in here, but we're going to break this down phrase by phrase, sometimes word by word, so that we can really understand what this definition means. So this p-value, the first word we see is probability, and that's what we're going to start with. All right, so we've talked a lot about probability in this class. In fact, we had chapters 5, 6, and 7 all dealt with finding probabilities. And one of the first things we learned about probability was our first rule of probability. And hopefully you remember this. So our first rule of probability said that all probabilities have to be between 0 and 1. And that is going to be one rule that our p-value will also hold to. It will always be a number between 0 and 1. Now, here's the tricky part. Sometimes our p-value will be so small that our calculator will want to give us a number that is in scientific notation. And so we have to be really careful with that and remember that that might happen. But if our probability has to be between 0 and 1, then when our calculator gives us something like this, it looks like 1.778, and I think, oh, wow, that's more than 1. But don't forget, if our calculator knows that it's calculating a probability and it's giving us something that will be between 0 and 1. So if you think you're getting something bigger than 1, always remember to go look at the far right-hand side and see what type of scientific notation we're dealing with. In this case, this p-value is actually, we need to move that decimal place 7 times. So that's going to be 6 zeros. And I guess if we round to 4 actual numbers that aren't 0. That'd be rounding. But, and how do I know it's 6, 0? It's always going to be one less 0 than my number, because my first move is always going to get me to the other side of that first number. So I'm always going to have one less 0 than what my scientific notation is when I'm dealing with a negative like that. So a p-value is a probability. That's our first part. All right, so our definition of a p-value starts out that it is a probability of observing a sample statistic. Now, we're going to pause there. Sample statistic. What are we talking about? Remember, our sample statistics are going to be our p-hat or x-bar. Now, there are tests that we're not going to cover in this class that would be the sample standard deviation. We're not going to worry about that, but you may see, like, just come up with the null and alternative hypothesis for standard deviation. And your parameters would be sigma, and your sample statistic would be S. But we're dealing with p-hat specifically in this section 10.2, and our parameters, so population parameters that we're dealing with, are, we're going to be trying to do a hypothesis test for a proportion or a population mean, mu. And again, we're not actually going to test, but if we were, it would be using the parameter sigma. So that's what we're dealing with. We're trying to test and see what's the probability that the value we get in our sample, and then the next part is we're going to keep breaking it down. So this is what we're looking at. We're using our sample statistic to see how extreme it is. How far away or how unusual may this value be. It may not be, but that's what we want to find out. All right, this next phrase is interesting because it works in either direction. So if you remember, we talked about having a one-tail test versus a two-tail test. What we're talking about when we say as extreme or more extreme, that's basically just saying if we have a value, and I'm going to draw a normal curve here so that we can have kind of the idea. Because whether we're dealing with the normal curve or the t-distribution, they both kind of have the same basic bell shape. And so what we're saying is we want to know if we have a sample value, so in this case maybe a p-hat, say my p-hat is sitting there. If I want to know what's the probability of getting a sample statistic as extreme or more extreme than the one I observed. So this is the one I observed. And I just want to know what are the chances that I get one that value or higher, or, see if I can move this up. Yes, I can. There we go. Slide that up there just a little bit. I kind of wrote in the middle and I need a little more space. So let me draw another normal curve. So that's one as extreme or more extreme. But what if my observed value is on the lower end? So we don't want to always say greater than or equal to, because if I'm looking for evidence, like we talked about when we were talking about coming up with our hypotheses for our hypothesis test, we want to look for what would give us evidence to help prove what we're looking to find. So I may not always need greater than. I may need less than. But that is as extreme, that's the solid line, or more extreme, that's the shaded area. And of course, again, in both cases, this p-hat, that is our observed sample statistic. And we've talked about how to find these probabilities. We've done normal CDF, and we've looked at how to find the area under a curve. Here's the cool thing that our calculators are going to do for us now. We don't actually have to go back and use normal CDF. What we can do is we can use just like we used on our confidence intervals when we did one prop z int and t interval, we're going to have the same thing that we can use for our hypothesis tests. We're going to have a 1-prop Z test and a t-test, and we'll see all those as we continue, but that's going to give us our p-value. But that p-value is just an area under a curve. It's just a probability of getting as extreme, so again, as extreme or more extreme, as extreme or more extreme. So it doesn't matter which direction we're going. That's what that phrase means. Now, all of this, of course, is contingent on the assumption that the null hypothesis is true. Remember, our null hypothesis is our statement of no change. So our statement of no change, or this is what we expect it to be for whatever reason. A lot of times, we'll assume that the population proportion is 50%. It's just, we expect that half are and half are not, unless we have reason to believe otherwise, and that's why we gather evidence. So this, we're assuming our null hypothesis is this population proportion, our known or assumed population value. And there are ways to come up with a standard deviation that we did not go over, again, because we're not doing those things by hand. We're just plugging it in our calculator, and luckily our calculator is really good about doing all this math in the background for us. It's almost like magic. But it calculates our standard deviation that we need, and then it finds this area, whether it's below or above. And I'm just going to draw one above. And it tells us what this area is, if, based on this population parameter that we're assuming from our null hypothesis, based on that being the true value. All right, so when we talk about a p-value, again, it's a probability and it's helping us figure out whether or not something is unusual. And let's say is unusually far away from what is expected. And really, I think that might be it. We may not need that third dash. It's just a probability that helps us determine whether or not we have a significantly, statistically significant sample that makes us stop believing the null hypothesis. So let's see what that looks like on the calculator, and then we'll look at a couple of examples.